Welcome everyone. During this lecture we're going to introduce the definition of density. We'll discuss a variety of pressure types including atmospheric pressure, absolute pressure, and gauge pressure. We will then explore an application involving gauge pressure. We will develop the relationship between pressure and depth within a fluid. We will then explore an application involving pressure versus depth in a fluid. We'll introduce Pascal's principle, we'll apply Pascal's principle, and we will conclude with an introduction of something called the buoyant force, as well as Archimedes' principle, followed by an application involving the buoyant force. Let's begin by introducing the definition of density. Density is a measure of an object's mass concentration with respect to volume. In other words, density indicates the extent to which an object's mass is concentrated or packed together within a certain amount of volume. The symbol for density is the Greek letter rho, and the equation for it is simply mass divided by volume, which we can abbreviate as m divided by v. From this equation we can extract the units. Of course, the mass units are kilograms and the volume units are cubic meters. And so the units are kilograms per cubic meter in the SI system. It's important to note that density values are tabulated within our textbook. For example, the density of water is given as 1,000 kilograms per cubic meter. So if we had a box whose volume was 1 cubic meter and we filled it with water, the mass of the water would equal 1,000 kilograms. On the other hand, if we filled the same box with aluminum, we would find that the mass of the aluminum is much greater than the mass of water. The mass of the aluminum would equal 2,700 kilograms, and that's because the density of aluminum is given as 2,700 kilograms per cubic meter. Generally speaking, when objects undergo a state transformation from liquid to solid, they actually get more dense. The exception is water. When water undergoes this transformation, in other words, when water solidifies and becomes ice, the density actually goes down. The density of ice is an anomaly. The value is 917 kilograms per cubic meter, and as you can see, this value is less than the value for the density of water. This is an important observation because this is what enables ice to float on top of water. We're going to find out later on that an object with a smaller density will float upon an object with a higher density. And this is what enables ice to float on water. We will now define pressure. pressure is a measure of the extent to which force is concentrated over a specific area. The symbol for pressure is P. The equation for pressure is simply force divided by area, and from this equation we can extract the units. Of course, the units for force are newtons, and the units for area in the international system are square meters. And so the units for pressure are newtons per square meter, but there's an alternate unit that we should be familiar with. The scientific community has named 1 Newton per square meter after Blaise Pascal. And so we will sometimes refer to the SI unit as the Pascal, and it's the equivalent of a Newton per square meter. Therefore, these units are interchangeable. As you can see, the Pascal is abbreviated as PA. We will now introduce atmospheric pressure. Atmospheric pressure is the average pressure exerted by the Earth's atmosphere at sea level. Now, we've all experienced the pressure of water as we dive deeper and deeper into a swimming pool full of water. Well, if we consider the Earth as a container full of air, coupled with the fact that we are immersed in this pool full of air, we can draw the conclusion that this pool of air also exerts pressure, just like the fluid in a swimming pool exerts pressure. The pressure that's exerted by the Earth's atmosphere, which we're going to label as P atmospheric, equals 1.013 times 10 to the 5th pascals. And remember, a pascal is just a Newton per square meter. If we converted this to the British system, we would find that this value equals 14.7 pounds per square inch. Which is sometimes abbreviated as PSI. What this tells us is that every square inch of surface, whether it's a square inch on your tabletop, a square inch on a wall, a square inch inside of your ear canal, or maybe the tip of your thumb, every square inch of surface that's exposed to the Earth's atmosphere will experience 14.7 pounds of force. That's very significant. That's close to 15 pounds of force. We will now introduce the definitions of absolute pressure and gauge pressure. Absolute pressure is a measure of the total pressure that is present at a specific location. In contrast, gauge pressure is a measure of the excess pressure above atmospheric pressure. And so the distinction between them is absolute pressure is a measure of total pressure, whereas gauge pressure is a measure of excess pressure. In other words, we're measuring how much pressure exists above atmospheric pressure at a particular location. We will now consider the relationship between these two pressures by considering a partially inflated tire. As you can see, our tire is partially inflated, and it's important to note that the atmosphere is exerting pressure at every point along the exterior of this tire. And so if we identify an area on the outside of that tire, the atmosphere is exerting a pressure. This area on the interior also is subjected to atmospheric pressure. If we carve out an area along the sidewall of the tire, that area is experiencing atmospheric pressure as well. Now, the pressure inside the tire is called absolute pressure. However, if we measure the tire's pressure with a tire gauge, it would not indicate the value of absolute pressure. Instead, a tire gauge would indicate the excess pressure. In other words, it would indicate the difference between absolute pressure and atmospheric pressure. This leads us to the following relationship. Gauge pressure is just the difference between absolute pressure and atmospheric pressure. We will now apply these principles within the following application. In this example, the tires of an automobile are inflated to a gauge pressure of 2.5 times 10 to the 5th pascals. If the contact area between each tire and the road surface is 350 square centimeters, in part A, we would like to determine the absolute pressure present within each tire. In order to find P absolute, let's first of all note that the gauge pressure was given. That value is 2.5 times 10 to the 5th pascals. Also, we established the relationship between absolute and gauge pressure. The relationship states that gauge pressure equals absolute pressure minus atmospheric pressure. P gauge, of course, equals 2.5 times 10 to the fifth. We're trying to find the absolute pressure. And atmospheric pressure was given as 1.013 times 10 to the fifth pascals earlier in our discussion. And so if we solve for P absolute, we obtain 2.5 times 10 to the fifth plus 1.013 times 10 to the fifth. And the result is 3.513 times 10 to the fifth pascals. In Part B, we would like to determine the weight of the car. And in order to do so, it's important to consider this area, the flat area of the tire that comes into contact with the road. That area, in our example, has a value of 350 square centimeters, which needs to be converted to square meters. Now, in order to find the weight of the car, we need to consider the flat portion of the tire, that flat area that comes into contact with the surface. That area looks like this. So here's a portion of the tire that is in contact with the roadway, and we need to construct a free body diagram on it. And so the first thing to note is that this portion of the tire is in direct contact with a column of air above it, and that column of air applies a gauge pressure onto the interior surface. Now, we need to represent the force, not the pressure. And so we will do so by noting that the force produced by the air equals the gauge pressure times the area of this footprint. We also need to note that the ground exerts a force against this flat region. That force, of course, is the normal. And the normal equals 1/4 of the car's weight. In other words, the car is in contact with the ground at the 4 tire locations. Therefore, each tire will support 1/4 of the car's weight, assuming that the car's weight is uniformly distributed. And so we will note that the normal equals 1/4 of the car's weight. We're almost ready to apply Newton's second law to this free body diagram, but first we need to convert the area into the proper units. Now, the area was given in the problem as 350 square centimeters. We need to convert this to square meters. We can do so by noting that 100 centimeters equals 1 meter. However, we need to square the conversion factor so that we obtain square centimeters in the denominator, which could then cancel the square centimeters in the numerator. This results in a value of 350 times 10 to the minus fourth square meters. We're now ready to apply Newton's second law. Let's note first of all that this pad of the tire is in static equilibrium. Therefore, if we add the forces in the y direction, they will equal 0. Notice that we only have 2 forces, so we'll extend 2 fingers from the summation, and we'll introduce the normal which is directed upward, minus the force exerted by the air. The normal equals 1/4 of the weight, which we can write as 0.25 W. The force of the air equals the gauge pressure times the area of this pad. Now the gauge pressure was given in the problem as 2.5 times 10 to the 5th pascals. And we just calculated the area as 350 times 10 to the minus 4th square meters. The product of the last two values yields 8750. And if we transfer that to the other side and solve for the weight, we obtain 35,000 newtons. Now you may be wondering why we use the gauge pressure instead of the absolute pressure in our calculation. As you can see, the force produced by the interior air was calculated through P gauge times the area. In order to understand this, let's consider this pad one more time. So I've enlarged this tire pad. And there's no question that the absolute pressure is being applied on the interior or the top surface of this pad. However, the absolute pressure equals the atmospheric pressure plus the gauge pressure. So we can represent the absolute pressure through two components. This arrow will represent the atmospheric pressure, and this arrow will represent the gauge pressure. However, the underside of this pad is exposed to the atmosphere. Therefore, the atmosphere is exposing atmospheric pressure to the underside. And the effect of this pressure results in the cancellation of the two atmospheric pressure components. And therefore, if we cancel these two arrows, the resulting arrow is just the gauge pressure, which is why we used it in our free body diagram. In part C of the problem, we need to calculate the magnitude of the normal force between each tire and the road surface. Earlier, we noted that the normal just equals 1/4 of the weight of the car, and so we will apply this equation to solve for the normal. Of course, the weight was calculated as 35,000 newtons, and the result equals 8,750 newtons. Which means that the road applies 8,750 newtons to the bottom of each tire. In part D of the problem, we would like to determine the magnitude of the absolute pressure in the tires if they are later punctured. In order to determine the absolute pressure, let's consider our tire diagram one more time. It's important to note that the absolute pressure will push against every surface on the interior of the tire in an outward direction. And so the absolute pressure at this location is directed this way, which is an outward direction. On the other hand, the absolute pressure on the inner surface of the tire will be directed in the opposite direction, which again is an outward direction. Let's now assume that this valve stem is faulty and that air is free to escape from the tire. Let's also represent a small amount of air near the valve that's about to exit the tire. The absolute pressure inside of the tire will push this column of air in an outward direction. However, since the other end of the stem is open to the atmosphere, the atmospheric pressure will actually try to push this column of air back into the tire. Since the absolute pressure in an inflated tire is greater than the atmospheric pressure, the absolute pressure will win this tug of war, and therefore this column of air will be expelled out of the tire. Now this process will continue so long as absolute pressure is greater than atmospheric pressure. But once absolute pressure equals atmospheric pressure, and this will occur, of course, when enough air has left the tire, once absolute pressure equals atmospheric pressure, no more air will escape from the tire. Therefore, the absolute pressure of a flat tire just equals atmospheric pressure. So we can note that the absolute pressure of a flat tire actually equals atmospheric pressure, which of course equals 1.013 times 10 to the 5th pascals. Let's also note that if we applied a tire gauge to a flat tire, that gauge would read 0. And that's because a gauge reads gauge pressure. It doesn't read absolute pressure. So again, a flat tire actually has a pressure of 1.013 times 10 to the 5th. However, the tire gauge will read 0, and that's because a tire gauge only measures the amount of pressure above atmospheric pressure. A flat tire only has atmospheric pressure within it, therefore the tire gauge reads 0. We will now introduce the relationship between pressure and depth within a fluid. Let's begin by introducing a container that's filled with fluid. There's our container, and the container could be filled with any fluid. It could be water, it could be benzene, it could be oil. For our purposes, let's assume that our container is filled with water. Next, we're going to trace out a column of water within this container. There's our column of water, and as you can see, this column of water is floating within the fluid inside of the container. Let's note that this column of water has a mass of m, And we'll also note that the top of the column is exposed to a surface pressure. Now, if the top of the container is open to the atmosphere, the surface pressure equals the atmospheric pressure. But that's not always the case. And so generally, we will consider the top pressure as the surface pressure, and we will call it P0. This pressure on the top surface is pushing down against this column of water. This column of water also has weight, and that's pushing the column of water down. So how is it that the column of water is floating? The column of water is able to float because the surrounding fluid exerts a pressure on the underside of the column that's directed upwards. We will refer to this pressure as P, and we will also note that this bottom surface is located at a depth h with respect to the surface of the fluid. Now, in order for this block to float, P must be greater than the atmospheric pressure. This pressure has to support not only the downward push of the atmospheric pressure, it also has to counteract the weight of the block. Therefore, this pressure will be greater than the atmospheric pressure. We have to answer the question of how much pressure is there at this location. We will answer this question by constructing a free body diagram on this block. Here's our block, and let's first note that the surface pressure is producing a downward force that we'll call F0. And F0 simply equals P0 times the surface area of the top. The block also has a weight which is directed downward. And of course the weight just equals mg. Finally, the pressure on the bottom surface of this block is directed upward, and it produces a force that we'll call F. That force equals that pressure located at the bottom surface times the area. This block is in static equilibrium, therefore if we add the forces in the y direction, they will equal 0. We have 3 forces, so we'll extend 3 fingers from this summation. We have the force on the bottom surface, which we called F. We have the force on the top surface, which we're calling F0, and we also have the weight. Now, this force F equals the pressure times the area. The force on top, F0, equals the surface pressure times the area. Before proceeding further with this analysis, we're going to derive a very useful equation that connects the weight to the density of the fluid. First of all, let's note that the weight simply equals m times g. Also, we learned earlier that density equals mass divided by volume. If we solve this for the mass, we obtain the mass equals the density times the volume. Now, the volume of this shape equals the area times the height of this shape, which we called h. We can also note the height in connection with this diagram. Again, the volume of this shape equals the cross-sectional area times the height of the shape. And so we can write the mass as density times the volume. Again, the volume equals the area times the height. If we substitute this result into the weight equation, the weight can be written as density, area, height times g. We will now substitute this result into the equation that we derived earlier. And so now we have pressure times area minus surface pressure times the area minus the density, area, height, g equals 0. Let's transfer these two values to the other side. That results in P times area equals P0 A plus rho A H times G. Now, algebraically, whenever there is a factor present in every term in an equation, that factor can be canceled. Notice that we have the area in this expression, there's an area in this term, and there's an area in this term. Therefore, we can cancel out the area. And as a result, we obtain P equals P0 plus rho G H. This is the equation we were seeking. This equation connects the pressure at a certain depth, which equals H, to the surface pressure, the density, as well as the depth. This is a very important equation, and it relates the pressure versus depth for a static fluid. Therefore, this equation can only be applied when the fluid is static. In other words, there's no motion within the fluid. P0 represents the surface pressure. Rho represents the fluid density. And of course, H represents the depth. Now, we noted earlier that when the surface is exposed to the atmosphere, then the surface pressure becomes atmospheric pressure. Also, under these conditions, the gauge pressure will equal rho G H. Remember, gauge pressure is a measurement of the excess pressure above atmospheric pressure. If we look at this equation, if P0 is atmospheric pressure, then rho GH is the amount in excess of P0. Therefore, rho GH is the gauge pressure. Under these conditions, this equation can be written as follows. And we will note that this last term equals P gauge. We will now apply these principles within the following application. In this application, we're going to determine the following for the container shown above, assuming that it is filled with water with its top surface exposed to the atmosphere. In part A, we would like to determine the absolute pressure at a depth of h equals 3.5. We can note, again, that the top surface of this container is exposed to the atmosphere, so the surface pressure, P0, equals atmospheric pressure. Also, the problem notes that we're seeking this pressure at a depth of 3.5 meters. Since the top is exposed to the atmosphere, we can apply this equation. P equals P atmospheric plus rho GH. Of course, atmospheric pressure equals 1.013 times 10 to the 5th. We now need to look up the density of water in the textbook. The density table in the textbook reveals that the density of water equals 1,000 kilograms per cubic meter. So our equation becomes 1.013 times 10 to the 5th plus 1,000. G, of course, is 9.8, and the depth was given as 3.5 meters. The result equals 1.356 times 10 to the 5th pascals. And that, of course, is the absolute pressure. In part B, we would like to determine the gauge pressure at a depth of 3.5 meters. The gauge pressure may be determined through this relationship. P gauge equals rho GH. The density, of course, is 1,000. G equals 9.8, and the depth equals 3.5. And the result equals 3.43 times 10 to the 4th pascals. And so if we carried a pressure gauge within a swimming pool and we dove to a depth of 3.5 meters, that pressure gauge would read the gauge pressure, which is 3.43 times 10 to the 4th, as opposed to the absolute pressure.